You have seats here, third row, second row. Just place here, one seat. I would ask please everybody to sit so we can start more or less on time. So in 5 past. Okay, so it's my great pleasure to present Slav. Slav has been with us for 12 years. I mean, every time with the school. I think when he joined, he was just 1 year into Google. Right now, he's a distinguished research scientist, the global director. He leads a huge team doing NLP work across the globe, has, of course, a ton of amazing work. And he always has the most insightful talks. So very much looking forward to it. Thanks.
Thanks, Ramon, for that kind introduction. And thanks, everybody, for organizing this wonderful event. It's always a pleasure to be here. And thank you all for coming. So this, when you saw the title, maybe you thought it was a typo, that there was natural twice. So hopefully in the span of the next hour, you'll get to see why I chose that title. I struggled a little bit with finding something succinct and appropriate. So as Ramon said, been coming here for a while, and the talks sort of in the early days and the whole summer school in the early days was organized around this classic NLP pipeline, where we would do different types of analysis in sequence, building up on top of each other, from part of speech tagging to dependency parsing to entity types and reference. And the hope was that by annotating sentences with linguistic structures, we would be able to reveal the meaning and make that information accessible for further processing for other tasks like question answering or whatever the application might be. And things have evolved quite a bit from that in the last few years, especially. And one exciting piece of work that came out this spring is this Palm Pathways language model paper from Google, where we have examples like the ones at the top, where a pre-trained model is just given the input there. There's a question with an answer, but the answer is not just the final answer. It includes also the reasoning of how to compute the answer. And then given just 1, 2, or 3 such examples, we can ask a question like, the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And the model is able to produce the string. The cafeteria had 23 apples originally. They used 20 to make lunch, so they had 23 minus 20 equals 3. They bought 6 more apples, so they have 3 plus 6, 9. The answer is 9. And I think just a few years ago, this seemed impossible to reach, or really unclear how we might build a system of that sort. Of course, this is not 100% accurate. It goes wrong. When it goes wrong really badly, and it's hard to understand why it went wrong. The arithmetic is not the arithmetic the way you learn it in school. Sometimes 2 plus 4 is 6, and 4 plus 2 is 7. The model doesn't really know the laws of arithmetic, but when it goes well, it's really impressive. And so that kind of brings me to the question of like, well, do we need these intermediate structures, or can we do everything with natural language? Can we express the tasks in natural language and provide feedback to the model in natural language and get away with these artificial concepts that are brittle and hard to reason over? So with that kind of context setting, let's take a step back and kind of speculate a little bit about how we got there and what might be needed to advance things further. So this is a chart of archive papers across different fields, and it's the same data presented in 2 different ways. One is the absolute number of papers, and then the other one is the relative number of papers. And you see the orange part, the computer science field, has been growing in absolute terms, and then in terms of relative terms, even more so. A lot of the other fields in the bottom are physics. Sort of HEP is high energy physics, and so the field is moving faster and faster. A lot of papers are being published, more people are joining, and there's tremendous progress. And in parallel with this quantity of work, we have also been increasing the scale of the models. And so here is a comparison between the number of synapses in different brains and the number of parameters in models that we have. And we still have a bit of a way to go to reach the size of the human brain, but the models have been becoming bigger and bigger. And with this scaling of number of parameters, we're observing scaling of performance. So this chart is a little bit hard to read, perhaps. What you have on the vertical axis is the relative improvement in machine translation quality, blue. And then on the x-axis, you have different languages, starting from languages where we have a lot of data to languages where we have less data. And then the different lines correspond to different size models trained on the same data, similar architecture, or same architecture. Like there's a dense one, and then the other one's a mixture of expert models of increasing size. And as you increase the size, performance goes up. It keeps on going up. It's expensive to train these bigger models, but it's also very kind of safe way to improve the quality of the models. So it seems like something we ought to do, while in addition thinking about how can we further improve the quality of the models, while perhaps reducing the size or the number of parameters, the amount of data we need. But overall, we're getting quite a bit of improvement from the scaling. And so last year's talk that I gave, also on the Monday, was called "Is Scale All We Need?" And back then, I actually argued that it's not all we need. And I still believe that it's not all we need, but also am much more optimistic about the benefits that we can get from scale. Because some of these developments that we saw in the last year, I would have thought they would take 3 years or more. And in part it is because we have these scaling laws that suggest that things will improve by 0.5% if you double the model size. And on average, that might be true, but we also observing nonlinear improvements and sort of breakthrough performance, where some tasks don't work at all. And then once you have a model of a certain size, things start working. And we don't really know why, but that opens up opportunities for improvements that are hard to anticipate. And so this year, my question for the talk is, are text-to-text models all we need? So can we have one giant text model where we put in text, define different tasks in text form, and then give instructions to the model or ask it to do certain things? And it's one model that can perform all the different tasks. And that paradigm is not new, but I think it might have been a little bit before its time. It didn't work so well in 2019, but now things are starting to work a lot better. And so before we go into that question in more detail, I thought I would take a small detour from sort of a practical perspective and talk a little bit about some of the misconceptions that I sometimes sense when talking to sort of switching between the academic community and the industry. So oftentimes we sort of conflate things and we simplify. And so we say, okay, well, machine learning model like BERT is being used in a product. So when the Google Assistant is answering your query, there's some NLP model and that handles your query and out comes the output, because BERT models have been used for question answering. So clearly, if you're asking a question, a BERT model can answer a question in the Google Assistant context. The reality, however, is a lot more nuanced and complex. So the way that we have the token versus type distinction in natural language, like the word book by itself is a type, But then depending on how it is used in specific contexts, the token might carry a different meaning. It might be a noun or a verb. And Google, perhaps we didn't do the best job of communicating these differences. We published a paper called BERT, and shortly after we talked about how BERT is being used to make search better. And it's easy to then say, oh, the model that was released is being used in search. And in practice, that's not what's happening. The model that was released was trained on public data and has a specific size and specific parameters that were trained, while the model that is being used in the product was trained on Google internal data. It's a model of a different size, and it shares the architecture and the modeling idea, but it's a very different set of number of parameters. And so in practice, what you see is that when you do exploration, like you train all these models, you figure out one configuration that works well, then you fine tune it for different types of applications. And then you distill it usually to something much smaller that can be served in production. And these are all BERT models potentially, or T5 models, or Palm models, whatever the latest flavor is. But they're all separate sets of parameters. And especially when we talk about responsible AI and best practices, I think it's important to be precise about these things, because a model that was published externally and that has certain flaws, it might imply that one needs to investigate models that are used in production, but one shouldn't equate the two, because the model in production doesn't share any parameters. It just shares the architecture, but not necessarily even the training data. And so I think in the academic community, rightly, there's a lot of work on responsible AI. I think in policy circles, there are lots of discussions about how do we regulate AI, and what is safe and what is not safe. And so I think it's important that we all have discussions about this and figure out a constructive way forward, and turn this into engineering and science as much as we can. These models are pre-trained on a lot of text. There will be good things and bad things in the data. Filtering the data and making the model blind to certain terms is most likely not a good solution. Because the world is not just a beautiful, peaceful place, but it has bad things in it. And the model needs to be able to deal with these things. And so we need policies that can be controlled and enforced. And we need to do the research to figure out what type of knobs do we need, and how do we enforce that when a knob is being turned in a specific direction, the behavior is observed. And so we've been trying to formalize this internally, and we're hoping to build this good cycle of things getting better, where we establish some objectives, and it's a multi-year journey. So we're not going to solve everything at once, but figure out what is the most important thing that we need to tackle first. Define a benchmark, a way to measure it. At the beginning, it's probably going to be based on human evaluations, but then once we have some human evaluations, maybe we can think about automatic evaluations to accelerate the progress at which we can do the research. And then once we can measure something, we can start mitigating it. And once you've mitigated some problem, then we can adjust our objectives and tackle the next ones and keep improving things. But for that, we need a common way of thinking about what the challenges are and how to frame problems. I'm happy to chat more about it. I have more questions than answers at this point, but this is how we're trying to think about it. And so in practice, what ends up happening is, because we don't have a clean solution, this is a slide from Microsoft. Google hasn't published anything like that, but our systems look very similar. Basically, you have many machine learned models that are used together in ensemble to filter the inputs, protect against certain types of outputs, and achieve a certain type of user experience that, when measured on live traffic, is deemed to be of sufficient quality. And they are kind of simplifying this and having fewer blocks and optimizing more end-to-end is likely to lead to improvements, but we need to be able to do this in a safe and responsible way. And so I think it's important to keep this in mind when thinking about machine learning in a product, that it's not just a model that is being exposed to the user inputs directly, but that there's a lot of other things that are happening along the way. So going back to the question, are text-to-text models all we need, or is something missing? Well, what do I mean by that? Like in your intro classes today, you probably had some equations along those lines where machine learning is about learning to map X onto Y with whatever function, linear function, neural network function. And as long as Y is from a discrete output space, it's relatively easy to evaluate how well we're doing. But once you move to a text-to-text paradigm, now Y is natural language. And so it's a large vocabulary of finite, but not necessarily short length. And you get this combinatorial explosion. And there are many ways that you can express the same thing. So there are many potential answers that are okay, and vast majority of things that are not okay. And so moving to a text-to-text paradigm makes evaluation a lot harder. Of course, people have been working on natural language generation for a long time, and we don't need to start from scratch. But I think it's important to kind of look a little bit closer at what's happening in the natural language generation evaluation space, and then what other implications that might have beyond the task as it is defined right now. So because language is so flexible, deterministic metrics like blue or whoosh are reaching their limits. And a trend has been to move towards learned metrics. So these metrics are not going to be deterministic. They will be imperfect, but because they're learned, they will be more robust and will be able to handle the variations in natural language better. And so some work that we did a few years ago looked at machine translation output, and we said, okay, well, can we use our language understanding systems in the context of language generation to do evaluation? Because understanding tends to be a little bit easier, so we might be able to detect whether two things mean the same thing, and train models for understanding and use them to evaluate generation systems. And the sort of naive approach would be to just take a pre-trained model like BERT and take human ratings data on a task where you say, okay, do these two sentences mean the same thing in the context of a translation? And then fine-tune your model to surface the learned metric. Turns out this doesn't work super well and requires quite a bit of fine-tuning data. But one way to mitigate it is to create synthetic data that is task appropriate. So in the machine translation context, you might be able to use round-trip translations to create paraphrases. You might systematically perturb the input in known ways and then create signals that tell you, okay, well, this is a good translation, this is a bad translation. And it doesn't have to be perfect, but it gives you large quantities of synthetic data that you can use for adaptation before you switch to human ratings. And that makes the model much more adapted to the task. And when you compare to other metrics, this type of learned metrics tends to have a fairly high correlation with human translations, which is what you, with human judgments of machine translation quality. And this is kind of what you would want from a learned metric. And so that, I think, has become a trend that like we have more and more metrics for natural language generation. The natural language generation field as a whole has exploded. There's a lot more work nowadays there. And that led to creating the GEM benchmark suite with lots of tasks and different metrics focusing on different aspects of natural language generation. But the problem there is that there's none of the metrics are perfect. And across language generation and language understanding, we've seen a proliferation of leaderboards. And leaderboards are good and bad. They're good because they get people focused. But at the same time, when people focus too much on a metric, they end up overfitting. In many cases, we are over the human level performance and people keep improving things, but it's not really clear whether fitting noise or whether we're making actual progress. And people stop doing the qualitative work and analyzing what is getting better and just focus on the numbers. And so there's a nice paper from our group looking at it at the various aspects of evaluation and the good and the bad aspects of it. But overall, I think like we need to embrace learned metrics because we won't have deterministic metrics. But even with the progress on learned metrics, I wanted to kind of pause and also kind of just ask a question of whether string to string generation is a good task to be pursuing, because a model producing a piece of text might or might not be what the user wants. Like if you ask a machine learned model, who is the president of Tanzania, and it gives you back some name, you have to trust it blindly. You can't like verify whether that's true or not, whether it's outdated or current. And so even if we have sort of ground truth evaluations for a specific fixed task in a real world setting, models that just generate strings might not be what we need. And so kind of here is a nice cartoon that I found, like, this like factuality, grounding, and deception, misinformation are sort of all these concepts that come to mind, whether it's malicious or not. Like many things are not white or black. There are nuances that depend on the perspective, and whether you see a 6 or a 9 depends on your perspective. We looked at some data a few years ago in a context of question answering, and there was a question: who was the first person to see planet Earth from outer space? And the most relevant article was a Wikipedia article about Yuri Gagarin, how he was the first person in outer space. And we got 5 ratings, and they were split whether Yuri Gagarin was the right answer or not. We ended up getting 25 more ratings, and there was still a bimodal distribution, because some people said, well, he was in outer space. Obviously, he saw Earth as the first person from outer space. And the other people said, well, I don't know whether the rocket he was in had a window. I don't know whether he looked out. The text doesn't say it. If I can reason and make that implication, but if I'm asked in court to testify, I wouldn't be able to say for sure. And I think the notion of a ground truth and something being objectively, factually correct is a tricky one. And it actually tends to apply far less than we tend to think. And so one way out of this might be to say, actually, we don't want just X being mapped to Y. We want an additional attribution, a list of references that we can look at and verify whether the Y holds. And that kind of breaks up the step of factuality or grounding into 2 steps. One is verifying whether between Y and A, an entailment relation holds, and whether A supports Y. And then a second step of verifying whether A is a trustworthy source. And that's going to be probably subjective, but it's something that we can then kind of, the Y to A mapping, we can evaluate, and we can build models for that. And then we can build separate models to figure out whether A is a trustworthy source, but that might also depend on the reader and the user to judge for themselves. We don't need to solve that with a machine learned model a priori. And so we released a paper just before Christmas, or at the end of the year last year, on arXiv with a formal definition of what we mean. I'm not going to bore you with the formal definition here to read it, but basically it boils down to an according to test. So for the question, how old was George Harrison when Wonderwall music was released? There's a supporting paragraph. George Harrison, born February 25th, 1943, was an English musician, singer-songwriter, blah, blah, blah. And his debut solo album was Wonderwall Music, released in November 1968. And so if then a model produces the output, George Harrison was 25 years old when his album Wonderwall Music was released. We can say that that statement is attributable to the paragraph, because according to the paragraph, George Harrison was 25 years old, which requires some arithmetic to figure out that 1968 is 25 years later than 1943. Sort of simple arithmetic, we say the raters can judge, but we might also ask the way that we saw it at the beginning, the model to produce that arithmetic, because maybe we can find a more exact date. And in this case, maybe 25 years old is actually correct. But if it was in January 1968, maybe it should have been 24 years, and we need to be careful with the months. And so that kind of then brings me to a different question. Well, can we trust these models to do arithmetic? And this is now a couple of years old. I think models have improved a little bit, in part because of the scale. But looking at GPT-3, it was kind of amazing that it could do arithmetic in some cases, but it was also super brittle, and just perturbing the arguments can cause things to flip. But you can see here this breakthrough performance where up till 6 billion, nothing works. Once you go to 13 billion, 2-digit addition and 2-digit subtraction starts working. And then once you go to 175 billion, 3-digit addition and 3-digit subtraction works. Extrapolating blindly here seems like a very wasteful way to try to solve arithmetic. A better way might be to train models that can use a calculator explicitly, that can extract spans that need to be used as arguments and figure out which function in the calculator to call. And this can be generalized to any type of APIs that we might want to provide, unit conversion and related things. There's been some follow-on work since this early work from our team, but I kind of just wanted to mention this as one example of a type of work that I think is good to consider doing, because we shouldn't blindly trust the model just to do the arithmetic, but to hope that these behaviors emerge. We can facilitate it by training models to do specific things. Another sort of example of things going well and bad, and this is actually more than a year old, and it hasn't been fixed. Ben Gomes is an early Google employee, but he's not 77 years old, as you can see also from the picture. And the reason that this answer is given is that there is a the machine learning system is not getting the references right, and it's extracting this from a conversation, from an interview where Ben Gomes is asking a question, and doing a demonstration, and the model is interpreting it as 77 years old being his age rather than Pranab Mukherjee. And so I think having that context is really important. When you just show this little sentence, it might seem correct, but showing the bigger snippet shows you that there's more. So, and that you shouldn't trust it. And similar things happen. This is another mistake that Google makes, is how many kids does Kamala Harris have? And it turns out that the Harris that is being quoted here is actually Nina Harris, who is the niece of Kamala Harris. And we just misunderstood that this Wikipedia page is about the whole Harris family rather than just Kamala Harris. And so understanding the context and the referential expressions is really important. And these models do get sometimes confused. And so when they produce just a string without attribution, it's a little bit dangerous to blindly trust them. Some work that we have done to kind of address this is what we call decontextualization. And it's a text-to-text paradigm where we are not trying to produce new annotations. We're not trying to explicitly resolve coreference. Instead, we're trying to train a system to rewrite sentences so that they can stand on their own, so that the referential expressions to previous sentences are resolved, and we can avoid such mistakes, or we can use such a system in an ensemble, as I showed at the beginning, where we can have the decontextualization system verify that what is being extracted and proposed as an answer makes sense, even when the sentences are kind of standalone, and catch problems where there's disagreement to flag it and to say, well, maybe we shouldn't be showing this at the top of the results because it's our confidence is low. And so we've created some data that we've released along with some baselines that we've trained in the space. And we are looking into then also extending this type of sort of text-to-text rewriting to something that we call QED for proof of work, where in the context of question answering, we have a question and a percentual passage that is answering it. And we're trying to rewrite the passage into blocks that make it very obvious how the sort of the reasoning chain is and what the referential expressions are, so that we can demonstrate that the answer that is being extracted is indeed answering the question that is being asked, rather than the passages being topically correlated, but not as oftentimes, like basically, oftentimes we don't, like when you look at quad style question answering, the models, they can extract the paragraph, but they can be easily fooled, and the answers tend to be right because the data set was constructed in such a way that the answer is contained somewhere. And in many cases, the strongest correlation tends to be the correct one, but not always. And so just because something is topically appropriate doesn't mean that it is answering the question. And so with a system like an approach like QED, we can break up this paragraph into predicate argument structures that we can understand and stitch together to convince ourselves that the answer is contained there. But as promising as this is, it also kind of brings a potential problem in that we're starting to trend back towards the more pipelined approach. It's all text-based. It's not symbolic anymore, but we are again sort of trying to build models for individual tasks that we stitch together, and things can become brittle. So finding the right balance, I think, is something that we need to pay attention to. And so one other potential way to do it is to provide some additional information about how the X and the Y relate. So in classic machine learning, you just give many examples of X and Y, and you hope that the system will generalize, because you might actually not even know what the right process of how they relate is, or you might not, like the whole job of the machine learning system is to figure out what the decision boundary is. But if you think about teaching in class or teaching your kids something, teaching a friend something, you wouldn't just give them 3 examples and say, now figure out the rest. You would probably explain how things relate so that one can generalize more easily and try to explain at the meta level what are the principles. And so providing kind of an explanation about the task and then this type of chain of thought prompting where we provide some reasoning are some examples of that I'll present. And I didn't know how to draw it in mathematical terms, so I just put the H on top of the arrow. It doesn't mean anything specific, but it's just some side information. And one could also combine this with the comma A attribution, and I think that's an exciting future direction. But for now, I'm not familiar with such work. We know how to evaluate attribution, but we don't have models yet that can produce attribution. And so some work from Google is kind of motivated by looking at how do we actually use these pre-trained models. We have 2 sort of dominant paradigms, pre-train followed by fine-tuning, or prompting or in-context learning. And then there's some variants of the prompting with fuchsia prompting or prompt tuning. But basically in the first paradigm, we clone the model and we adapt it to a new task. by shifting most of its parameters. And in the second one, the pre-trained model is fixed. And the context is used to demonstrate what task the model should perform. And in this work on fine-tuned language models, our zero-shot learners, the idea is to tune the model for many tasks together and then do inference on a new unseen task without additional tuning. But because the model has been sort of predisposed for what is going to be asked, it is better suited for that. And one reason why I'm excited about this and wanted to highlight it here is that the task definition is done in natural language. So the tasks, like they evaluated on 62 different tasks that were clustered into groups. And then for the different groups, a template in natural language was written where for entailment, the template is, here's the premise, then follows the hypothesis, and then there are the options, yes or no. And then for other tasks, there would be a different template, but it would express in natural language what you want the model to do. And the model then can sort of be instructed in natural language to perform new unseen tasks. And some of the generation ability seems to be coming from exactly how these templates are formulated. When you formulate them differently or with less intuitive terms, performance drops. It's more of an art than a science how to write these templates, and in general how to write these few short prompts. So that's a limitation, but it is also compelling because you can just express your tasks in natural language rather than in some symbolic way. And so this idea, I think, carries them forward, and Jason Wei is first author on both of these papers, carries forward to this chain of thought prompting idea where instead of just providing input-output pairs, we write an explanation that allows the model to understand to some extent how the input and outputs relate, even though these are just strings and it's not a symbolic representation of the mapping function. It seems to predispose the model and to lead to much better performance. So if we look at the direct prompting versus chain of thought prompting, basically the dotted line or a dashed line versus the solid line, and then these horizontal lines are the best results from prior work, and we see significant improvements from the chain of thought prompting, and in many cases the result then ends up exceeding the state of the art from prior work. So in the Palm paper, we played around with this quite a bit, and Jacob Devlin came up with these nice joke explanation examples. And I don't know whether you've seen the paper. In that case, you might be bored by the joke, but I'll still read it because I find it fascinating. Did you see that Google just hired an eloquent whale for the TPU team? It showed them how to communicate between two different pods. If I tell this joke to my parents, they don't think it's funny. They don't get the references. They don't really know what's going on. And it's therefore, for me, even more impressive that this model produces the following output. TPUs are a type of computer chip that Google uses for deep learning. A pod is a group of TPUs. A pod is also a group of whales. The joke is that the whale is able to communicate between two groups of whales, but the speaker is pretending that the whale is able to communicate between two groups of TPUs. And I think just a year or two ago, like these types of fluent and coherent generations were fairly unthinkable. Now, maybe we found a lucky sort of configuration that the model is really good at joke explanations because they're kind of maybe a fixed set of types of jokes, and maybe there are lots of joke explanations in the training data, and it has learned patterns. But even with all of those caveats, this is a unique joke that is not on the internet. It was made up for the purpose of the paper. And the model was able to pull together information from various sources and to stitch it together into a very coherent explanation in ways that I don't know whether we would have any other system that can do things like that. And so I think it begs lots of questions of how do we get to control that behavior? How do we get that behavior at smaller scales? How do we get that to work in other languages? When you tried it in other languages, it's working, but not as well. The sort of the amount of training data in English is certainly playing a role. And so how can we make these models more multilingual and get them to also explain other things beyond jokes? So when we don't know what to do with the models, we try to sort of look at the parameters and see how inputs relate to the outputs and how things are embedded. And so I wanted to make a brief plug for the language interpretability tool, which is an open source model or tool that we have released and that we constantly extend, where we're trying to have sort of a more or less complete suite of techniques that have been developed for understanding model behavior. But even there, it's oftentimes unclear. What do we mean actually by understanding models? One idea might be that for a given input sentence, one wants to see which are the most important terms that trigger a specific prediction. And that can be helpful in certain contexts, but in many contexts, that's not sufficient, because just knowing that a particular word triggers a certain classification label doesn't explain why the model is putting so much weight on that particular term. And so in those cases, it might make sense to go back to the training data and retrieve relevant training examples that demonstrate why the model has learned certain types of patterns. And when we go to these pre-trained models that have seen billions of tokens, doing this in a scalable way is non-trivial. But I think it's important to think about sort of what are systematic ways that we can analyze these models, understand how the input data affects final model behavior, and then going back to this controllable policies question, like how can we then turn it around and say, okay, well, the data had these things, maybe we need to change the data distribution, but maybe retraining all the time is not going to be feasible, and so we need to be able to modulate things once the model has been trained by changing certain types of priors to upweight or downweight certain behaviors. And for that, we need research to figure out how to do these things. So summarizing, I think text-to-text models are quite promising, and they can allow us to do many things in a very flexible way. But if we want trustworthy NLP, we need to be able to build trustworthy systems out of untrustworthy components, because some of the components won't be you can't give them a seal of approval that they're safe under all circumstances. And we need to sort of all work together to evolve our framework of how we're thinking about these problems, to build techniques that allow us to expose problems, measure problems, mitigate problems, and then repeat. And we need to also not assume that the tasks, the way that they're defined, are fixed, but we need to be willing to think outside of the current paradigms of sequence to sequence and say, well, actually, a different type of task formulation might actually be more productive and safe in the long term. And even if it means that we need to reset things, it is going to be viable for the longer term. And then finally, and I might have made some mistakes along the way myself by using sort of expressions that try to, that accidentally anthropomorphized the technology, basically gave it human characteristics. I think we oftentimes say, oh, the model is thinking or has read or something, but these models, they're not active agents. And I think sort of when speaking to other researchers, it's usually innocuous and doesn't do much harm. But when we speak to non scientific audiences, I think this creates expectations that are unwarranted and that can worry people as a result. And I think as researchers, I think we need to stick to the facts, and in our academic writing especially, stick to kind of objective statements and not put unnecessary sort of fuel into the fire and get people worried. Because these models are far away from having human qualities, even if on a specific narrow task, they can perform tasks maybe as well as a human. So with that, I'll stop and open up for questions, and I'll leave a few more joke explanations up if you want to. Don't be shy. Somebody has to be the first. Thank you, Noah.
So we've done very interesting models. And I'm going to always use the topic here to ask it, like forcing teachers questions. Right now we're very optimistic on language models, right? So there's this whole idea that language models get their from text, and that's going to eventually another round, right? And it's impossible that just from text language models can basically learn about the world. And the alternatives don't seem to be, there doesn't seem to be like a winning alternative to that. Do you see in the coming years the possibility of a language model research in the sense that maybe GPT-3 or let's say GPT-4 is the best we can do? Yeah, this language, and then suddenly we realize that to escape that, we have to fundamentally come up with something new that will take some time?
Good question. So short answer is no. Longer answer is basically, I think a few years ago, I was sort of fairly certain that there's quite a bit of headroom just in the language modality alone. I think there's still headroom in just doing language pre-training based on text. But there's more and more work in the multimodal space happening as well. And I think maybe in 2 to 3 years, the majority of the work might be multimodal. So maybe you'll say it's a winter for the text-only models, but I think that for the field, it's just gonna all come together. And there's some exciting work happening on language and speech joint training, as well as on language and image work. I was talking to Andrea earlier that would be great to pre-train models on video where language is situated in a visual context. I think a lot of the ideas are around. In part, I think it's a computational challenge. And sort of like if you think about transformers weren't around, but the idea of discriminative language models is not a new one, right? Like it has been around for decades. It's just we didn't have the computational power to do it. We didn't have enough data to train these models on. And so one could say it's not a new thing, sort of a causal LM. People have been trying to train that since Jelinek. And so I think with the image stuff, we're seeing similar things that things are starting to work, but we need alignment across the communities about what are the right tasks to focus on and how can language has shown quite convincingly that scaling brings quality gains. I think in the vision community until recently, it wasn't as clear that just making the model bigger would necessarily make it better. I think they're getting there now because some tasks are being defined. Basically, the tasks were too simple. If it's just image classification, cleaner data trumps more data. But once you go to higher level tasks and you want to not just label objects, but explain relationships, bigger models tend to do better. And I think the question there is going to be also sort of a research and engineering question, like, do we train joint language vision models together from the beginning? Or can we train a language model and a vision model, put them together, and then train something on top of that leverages these representations that are modality specific and fuses them late? And the engineering questions here, I think, are non-trivial and might imply also, might impact how progress is made. Because if you have to train everything from day one at the beginning. It's just going to require a lot more coordination. But if you can do things separately in parallel and combine them later, then you enable people to make progress independently. And I think we need to investigate how to do this. And I think that will be what sort of will transition when we see the headroom disappearing and the gains leveling off. I think we'll start just doing more multimodal stuff, and hopefully things will continue. But I'm an optimist, so I could also be wrong.
Thanks for the great talk. So to anthropomorphize a little bit, so these models seem to be not very good at knowing when they don't know. Right? So if you ask them a stupid question, say, when will the Eiffel Tower be turned upside down? It will answer something, right? So is that because they don't do any confidence estimation about their outputs? What would it take to make them say that question doesn't make sense?
That's a great question, and that's something that we recently talked about internally as well in the context of question answering, because there's basically no negatives for that. Like they only see the positives things, and things that humans with common sense would just say, oh no, that doesn't make sense, it's not going to happen. They haven't been trained. And so I think part of the answer could be that we need fine-tuning sets that include explicitly stating certain things that don't make sense, so that the models become more robust for specific narrow tasks. But then I think to solve this in a more general setting, I think we might need more significant changes, and like to be thinking also about causality and getting better at the confidence estimation, as you were saying. There is some work on causality. It's right now sort of not integral, or kind of not integrated into these models, but I think we probably will need to tackle it at some point, but it's really hard. Yeah.
Cool. That's one from Sheffield. I was wondering, the model seems to get larger and larger, and do you think that's where we should go in creating larger models? Because I mean, as a researcher, I wouldn't be able to do that unless I worked with Google, for example. So do you think we should try to find ways of scaling down, or these achievements kind of show that it is possible, but we just need to put on more work to actually make them smaller? Like, where do you think things will go in the future in terms of both industry and maybe smaller scale research?
It's a great question, and I think it's sort of multiple forces come here to play. I think we can just keep growing the models and things will get better up to a certain point, but it's going to be very expensive and we'll get into diminishing returns. So we need to figure out how to get better performance at a fixed size or perhaps at a smaller size. And there was this chinchilla paper from DeepMind that was I was very happy about, because they showed that our models are undertrained, and just training a smaller model for longer is a better way of using your compute than training an even bigger model. And that in a way took us kind of in the right direction. Like it saved us maybe an order of magnitude in terms of model size. And we need to just sort of repurpose how we do the computation. I hope I pointed out also some problems that are not only kind of solvable by scale, because I think there are lots of other, like lots of these problems about control and explanations and other things. They'll get better when you have a bigger model, but they can be addressed at a smaller model size, and so you should be able to work on them in an academic setting, especially if they don't require a new training from scratch, but working with a pre-trained model that has been released either by the Big Science Initiative or by other industry labs, and so it's kind of, in the last years, it's become sort of the type of research that you can do in academia versus the type of research that you can do in industry has kind of, that gap has widened a little bit. It used to not be there as much. But I think there's still a lot of work that can be done at the small scale that is relevant. And then it's more on the people kind of after you complete your education to see what type of work do you enjoy more. Do you enjoy working on a big system with many people, or do you prefer a more controlled environment where you can set the parameters and really kind of develop techniques that provide certain types of controls that in a messy large language model setting, you kind of have to just be a bit more hand wavy. And these things will, I think, sort of take turns and hopefully we'll be moving together forward.
Hi, I also have a question, like to go further onto the big models problem, just maybe a word on the ecological impact of such big models. Yeah, everyone's found the best results are usually obtained with the biggest model, but we have all these questions currently about the environment, and I know you have a few words to say about this.
Yeah, I mean, I think it's important to think about the environmental impact. I think, however, I think the discussion is, I think it's important that we include sort of statements that estimate how much compute went into papers and we openly disclose it. I think in many cases, sort of, I don't know how many of you are from Portugal and how many of you flew here, but the emissions generated by all the flights, oftentimes, like for a big conference like NeurIPS, probably all the people getting together is causing more CO2 emissions than the models that are being published. And that's for two reasons. One is that many companies are pretty good about placing their data centers in places where there is renewable energy. And Google, for one, has been committed to being carbon neutral for a long time, and we buy offsets, but we hope by I think 2025 to be like 24/7 carbon neutral. But then beyond that, the other thing is that with these large language models, like for the small ones, we run many experiments and we try out different configurations. When we train the large models, we train it once. So it's literally like the Palm 530B model. There was one model that we have ever trained at that scale. So it's not that we have 15 of them lying around and we publish the best one. It's literally that one. And so I think we need to think about it, but I think data center emissions, I don't think are our main issue. It's my perspective.
Thanks for the great talk. You touched a little bit about it and you started talking about evaluation. And I think it's also great, but then whenever we get to evaluation is when we are sleeping a bit in terms of NLP in general. And it's really hard to evaluate something like this. How do we know it's good or bad? Or even with Mario's question about when it doesn't know when it's wrong, right? So do you have any insights on what's the future of evaluation on this kind of things, whether we can actually simplify into one single metric, or we should be looking into a multitude of aspects?
I agree that it's really hard work. It's really important work. We don't have enough of it. I think it's not valued enough in the academic community. And my personal answer is that I think we need a multitude of metrics. I think it's going to be hard to bake things into one number. As engineers, we like to have one number that we can hill climb on, but I think it's impossible to get fluency and accuracy and all the various aspects into just one metric. So I think we'll need to do different ones, and it's going to be some combination of learned metrics and human evaluations. So I think in academia, it's much more easy to work with a fixed data set and a metric that you can run, because you don't and even in industry, you don't want to wait for the human raters, but at least in industry, most products use human evaluations. And so we have the pipeline set up. And I think doing a PhD program, you want to get done in a certain amount of time. When you're in an industry setting, sure, there's time pressure, but you're also not, like, if you miss a conference deadline, there will be the next one, it's fine. You don't need to graduate. And so I think we can sometimes approach things a bit more with a long-term perspective. And I think many people embrace human evaluations a lot more. And so I've been also encouraging my team to think about, can we set up leaderboards with human evaluations for academics where, like, let's do the math, like how expensive would it be to do a human evaluation for a submission? And if it's $50 to $100, maybe we can foot the bill and it's going to be fine. Like at the end of the day, Google gives out grants to faculty, and instead of giving a grant, we'll do a grant for a leaderboard, and we'll get better and kind of evaluation of the systems, and we'll understand more what is working and what is not working, because the automated metrics cut too many corners. And so we'll see how things will evolve, but I do think that humans will have to play a role in the evaluation of these systems. Any more questions?
Hi, so thanks for the wonderful talk. Just a general question. So we have obviously the large language models with billions of parameters, but how many of these parameters are actually useful in the model themselves? Or is there any optimization to be done on the parameters themselves to reduce the size of these parameters and this sort of stuff?
Yeah, very good question. And I agree with sort of the implied premise that many of them are not useful. We see that there are lots of sparsity patterns emerging. I think one answer is that sort of sparse models might be a better way to go. And we're like some of the machine translation results that I showed at the beginning were with sparse mixture of experts models. And we have a lot of work on sparse models. I think there's room for improvement on the type of sparsity that we have in the models. We have these mixture of expert models where the experts are all equal size. And it gives you some computational advantages at inference time, but I think we probably want something more flexible. Certain words might require more computation than others. And so having variable sized experts, figuring out how to train the models in a more flexible way, perhaps start with a dense backbone and then add sparsity as you go, or sparsify components. In general, I think, and that maybe goes also back to the carbon footprint question, I think we will start saving a lot more when we figure out ways to reuse existing models. And I was talking about that with Amal's question about reusing a model rather than starting from scratch when we train it. And right now, in academia, just because you want to control things, you always start from scratch. You don't start from a model and continue training it. But that's extremely wasteful because we're throwing away all the things that the previous model learned. And so we are looking into component reuse and modularity. And can we take BERT, PALM, whatever models we have, and then continue training from those parameters, or initialize or bias in some certain way, so that we don't have to relearn the things that the model has already learned. And then I think thinking about sparsity in that context makes also a lot of sense. But I think we've only scratched the surface in the type of sparsity that we've explored, and there are some benefits, but I think we'll see more benefits when we have more flexible sparse architectures.
Otherwise, hi, thank you for the talk. Just one quick question out of curiosity. On the earlier, one of the earlier models that you showed that did this kind of chain of thought but for math problems. I was just thinking, if the model comes up with like a chain of thought that might be wrong, but comes to the right answer, like, is there a way that you guys can verify, well, this is a stupid chain of thought that got into the right answer? or maybe it's just a way to solve a problem that you didn't think about? Is there that kind of thing in the evaluation or?
No, so I mean, for the chain of thought stuff, right now the evaluation is only on the final answer. And so I think we need to extend the evaluations to actually also look at the reasoning that went behind it. And for example, these are cute to look at, these joke explanations, but we have no way of saying, is this right or not? Is this meaningful or not? Is it missing something? And I think one thing that we also sort of, as a community overall, I would say struggling with is getting into a more iterative mode of operation. We do things one shot, like you do an input, you get an output, you evaluate. But the real world is much more interactive. And I think when something goes wrong, figuring out how to give feedback in natural language and get the model to adapt to that, I think is really interesting. I think people are starting to look at it in the context of image generation. DALL-E and similar models like Google published these models, Imagine and Party. The way that you play with them is that you put text in, you get an image. When you don't like the image, you change the prompt that you put in, but you restart. And it would be much more natural to sort of, you start with text, you get an image, and then given this image, you add a bit of text, and then the model takes the input, the image as an input, and modifies it for you. And so we could envision doing something like that here with text models as well, that you give feedback and say no. But what we do is we do few shot examples where we then go back and change the few shot example and the template, but we are not explicitly addressing the mistake that the model made because we don't have the techniques to do that. And I think that, again, is something that can be studied at a smaller scale. It doesn't need huge computation. It's really hard to evaluate, to go back to the other question of evaluation, because now it's a dynamic system. It's not a static eval set, but depending on the model output, you might have a different reaction. And then it's hard to know how to evaluate these dynamic systems. But I think in practice, if we can make progress on that, that would be really useful.
Hi. How did you evaluate the factor correctness in case of these column setups that you just showed these explanations? That would be interesting.
We have not evaluated. These ones are just anecdotal.
No evaluation of factor correctness in this case.
I mean, I don't know how to do it. Like, I think we're thinking about it, but these are really sort of anecdotal ones, just to show kind of, they're not like super cherry picked. Like, it tends to work 19 out of 20 times that it produces something coherent, but we don't, like, they're for you to evaluate. That's why we have a lot of them in the paper. And it's you make up your own mind whether they work or not. But we need to systematize it. And that's why I wanted to draw attention to the need for evaluation with context and references, or even without. But kind of, is this the only explanation? Is it the best one? I think it's not a binary thing. It's a spectrum, probably.
Okay, so